All right, you guys. So for the first half of this course, we've been spending a lot of time primarily focusing on big things, right? So most recently, ecology, before that, evolution. Um, but it's time for us to start to get tiny, okay? And so where we start with that, understanding the tiny parts of biology, is we have to start with chemistry. And some people are like, ugh, chemistry. Some people love chemistry. But you know, whatever your feelings are about chemistry, you might be wondering why we have to spend so much time talking about chemistry in a biology class. Well, fundamentally, you know, living things are just a fancy kind of chemistry, essentially, right? We're basically just bags of chemical reactions. That's what life is, okay? So we are going to start with the chemistry of life, or molecules of life, or whatever I called it in Canvas. Okay. So we're going to start small. A lot of this stuff you probably know, at least things in the beginning. So we're going to break this video up into a few different sections. We're going to just do like kind of the basics of chemistry. And then we're going to focus a little bit on specific types of molecules that are found in living things. Okay. And some of this is going to help you really appreciate more what you were learning about when we were talking about the origin of life. Okay, so I'm going to try to refer back to that. Okay, so just as like a little reminder, you know, fundamentally the basis of life is chemistry. And so that's why we're starting here, right? So we've already we've done a lot of this already, right? And so now we're starting down here and we're going to kind of work our way up, or kind of spend a lot of time in this general vicinity for the rest of the class. Okay. It's exciting. We're halfway. We're moving along, doing things. Okay. So, like I said, a lot of this is just real kind of like basic physical science, chemistry stuff. So what is matter? Matter is anything that has mass and occupies space. Okay. And so I think most people fundamentally have an understanding of that when it comes to solids and liquids. Gases are a little bit trickier because you can't see them, right? And so, at least many of them, you can't see. And so it's a lot kind of harder to convince yourself that that is a substance, but in fact it is, right? It takes up space and it has mass. So gases count as matter as well, okay? Matter is made up of elements. Elements are the smallest units of matter that maintain their proper, that what do I want to say? That can't be broken down into smaller groups and still maintain their properties. So yes, elements are made up of smaller particles, right? But elements are sort of characteristic units of chemistry, okay? And so everybody, we'll come back to this in a second. I know how much you all love the periodic table. No, you don't need to memorize this. In fact, you don't need to really know that much about how to look at it, other than the periodic table is a list, essentially, right? It's a table that includes all of the different known elements. And in fact, this one is missing, it looks like a couple of the newest ones, right? Because they're able to produce more in a lab under weird, like artificial, conditions. But this is pretty up to date. And they're arranged in a very distinct pattern because of characteristics of those different elements. I don't really care if you know any of that. That's cool. But I do expect you to be able to know what each little box tells you, okay? So, for example, here is the little box from a periodic table for the element carbon. We're choosing carbon because it's a really important element in living things. Okay, we are in fact carbon-based life forms, as some people might say. So what information do we have on here? So usually you'll see the name of the element, which is useful. Okay, and then a symbol. The symbols are typically one letter, though you know, eventually you run out of letters. So many of them are 2. When they develop new ones, sometimes they have 3 letters for a hot minute until they give it a better name, right? But typically they're 1 or 2 letters. And so some of these you'll get used to seeing enough that you'll learn them. But like, yeah, I don't expect you to memorize them or anything like that. Okay. So, right. So the letter is the symbol. Okay. The number in at least in your book, okay, the number that's above the symbol is the atomic number. Okay. And what that means is it refers to the number of protons. Okay. Now that's one of the subatomic particles, which we'll talk about in just a second. This is essentially the definition of each element. So each element is defined by its atomic number. So carbon has the atomic number 6 all the time. Even different variations of carbon, they always have an atomic number of 6, period. Okay. And so if we go back and look at the whole table, right, you can see, I know they're kind of small, right, but you can see there's carbon, there's the 6, there's nitrogen, there's oxygen, hydrogen. These are shown in orange because these are some of the real important ones for life, real big ones for life. Same thing with the pink and the green as well. Okay, so that number on the top, like I said, it's called the atomic number, and it essentially is like the defining feature of each element. And if it changes, then you're talking about a different element. Okay, atomic number is the number of protons. So carbon always has 6 protons. We'll come back to what a proton is in a sec. The second number is the atomic weight, or sometimes people say the atomic mass. Okay. That is not always the same. That can vary. Okay. And so what the atomic weight is the number of protons plus neutrons. Neutrons are another subatomic particle that we will come back to. Okay. So we'll talk about what those particles are in just a sec. Okay. So that's what's in the little square. Okay. And so we'll refer back to all of this in just a second. Before I forget though, the reason why we have symbols is as a way of shorthand for talking about chemicals, right? Talking about reactions and talking about our different elements. Okay. So typically the way that the names of chemicals are written in shorthand is using those symbols from the periodic table. All right. You also see numbers associated with these. Okay. So this is an example of a chemical reaction, right? So a chemical reaction typically is when you have some things and they turn into something else. Okay. What you start with are called the reactants because they are going to react with each other. Okay. And the reaction occurs and you end up with the products of the reaction. Okay. So in this particular example, we are looking at a chemical reaction where glucose and oxygen are the reactants. And after a particular chemical reaction occurs, and I'll tell you later what that chemical reaction is. It's actually a series of reactions, it's not just one reaction. You end up with the products of water and carbon dioxide and some energy. Okay, so what do all the things mean here? So we already talked about what a reactant is and what a product is. There's always an arrow showing the direction that things are going in, right? Okay, sometimes you have an arrow that goes back like this too, because it could go this way or that way. Okay. All right. How do we read this? So whenever you see a number that is a subscript, so below the letter, that's telling you how many atoms of that element there are. Okay. So glucose, we're just going to focus on glucose for a second, has 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Okay. Cool. For oxygen gas, now we have a number in front of the letter. What does that mean? Well, this is what the molecule looks like. So it's two oxygens, two atoms of oxygen that are stuck together. The 6 in front tells you how many of those you have, how many molecules, okay? So numbers that are subscript tell you how many atoms of any given element there are. And then if there's a number in front, it implies you have some number of molecules of that particular atom. If all of this is like, wait, whoa, slow down, what's the molecule? We'll get to that in a second, okay? I just wanted to kind of lay this out so you have this in your mind before we go through all of that. Another thing that's useful to know is you should think of numbers that are in front of the letters as kind of the same way that you would use them in like algebra, right? So if I put parentheses here like this, right? What the 6 means is that you have 6 molecules of water. Well, each water molecule is made up of 2 hydrogens, because there's a 2 after the H, and 1 oxygen, because there isn't a number down there. So, you know, by default, it's 1. And so what that means is that you have 6 of those molecules. So actually, in total, this ends up being 12 hydrogens and 6 oxygens, because you have 6 of those. Anyway, okay, we'll get into this a little more in a second, okay? So they're showing you pictures of what the molecules look like. They're showing you sort of the shorthand way of writing this stuff. We're not going to be doing a ton of this, so don't panic if you're like, oh my God, I took chemistry once and it scared me and it was terrible and I don't want to have to balance equations and blah, blah, blah. Don't panic. We're not going to do a ton of that, okay? All right, so where were we? Right, so elements are made up of atoms, okay? So the biggest elements, the elements that are the most abundant in living things are oxygen, hydrogen, nitrogen, and carbon, okay? You don't need to memorize any of these percentages. Just realize, right, that it, you know, if we separated you into all of your individual elements, right, 65% of you would be oxygen, right? Well, I can't read the, sorry, my little bar's in the way. Almost 19% of you would be carbon, right? 9.5% hydrogen, a little over 3% nitrogen. And then there's some stuff that's also, you know, not super, it's not super abundant. So those percentages are smaller, but they're still significant, right? And so when you're looking at this list, you might notice, well, some of these things are things that I find in my vitamins, right? Like, oh, we're supposed to have calcium in our diet. Oh, we're supposed to have phosphorus and potassium and, you know, and magnesium. That comes in a vitamin, right? And then you also have these trace elements that are, while not very abundant, still vital for life, okay? So there's this cool little diagram, which I kind of enjoy. And so remember back on the periodic table, how it was orange, pink, and green, right? So orange are these, pink are these, and the green ones are those, right? And there's cute little pictures and whatever. You don't need to memorize these, okay? This you probably should, you should be able to remember that, right? Oxygen, carbon, hydrogen, nitrogen. You should be able to know that. Don't memorize the periodic table, okay? Anyway. All right, so let's talk about the makeup of any atom. Okay, so atoms are made up of subatomic particles. Sub meaning like below. So subatomic particles are particles that are smaller than an atom. Subatomic. And the easiest way to look at these things is to use little diagrams. Now, the problem with these diagrams is they're not really super realistic about what atoms actually look like, but whatever, okay? This is how we visualize them, okay? So each atom and the inside of the atom has a structure called the nucleus. Now, one thing that is pretty confusing that I don't want you to get confused by is the nucleus of an atom is much smaller than the nucleus of a cell. So they are not the same thing. The word nucleus basically just means the center of something. So we can use the word nucleus a bunch of different ways to mean the middle of something. So this is not the same nucleus as the nucleus of a cell. This is the nucleus of an atom, okay? So an atom has a nucleus, and the middle part of the atom contains the protons, which have a positive charge, which is why you see that little plus there. And the neutrons, which are neutral. They don't have a charge at all, okay? So those are in the middle. Around the outside of the nucleus, there are electrons. Electrons have a negative charge, okay? Now, some things to know about all of this. Electrons are so small that we essentially, they do have mass, but it's such a small amount, we don't even really include that when we're talking about the atomic mass or the atomic weight of a particular element, right? We sort of ignore it, okay? Because they are so incredibly small, okay? Whereas protons and neutrons are essentially the same mass as each other, okay? All right. Come back to that in a second. So in this example, we are looking at, what are we looking at? In this example, we are looking at an element that has 2 protons, it has 2 neutrons, and it has 2 electrons, okay? So first of all, what element are we looking at? How would we know that? How would you know what element you're looking at? Do I even know? Oh, I had like 3 sips of water. It doesn't have to be a short lecture. Okay, so what piece of information do we need to know in order to figure out what element this is? So remember, there's atomic number and atomic mass. So atomic number is the number of, that's all scribbly, you can't read it, is the number of protons. So how many protons did we have in this example? We had 2. Okay, so hold that in your brain, 2. All right, we gotta find, I know it's too little for you to see, right? We gotta find the one that has 2. And so even though there's a gap, it always reads from left to right. So 1 is here. Oh, look, here's the one that has an atomic number of 2. And then what is this down here? Uh-oh, I'm getting interrupted. Hold on 1 second. What are those high interruption days? I seriously don't remember where we were. Other than we were talking about how the example that we were looking at had it had 2 protons. And so remember that the number of protons, right, which is the atomic number, is sort of the defining feature of an element. Okay, so the element that has 2 protons is helium. Yay! And it is abbreviated He. Okay, now that number on the bottom there, I know it's tiny, but if I copy this bigger, it says 2He, helium, and then it says 4.003. So we know this is the atomic number, right? What's this number down here? What's the 4.003? That's right. It's the atomic weight or atomic mass. I do slip into mass because that's what I prefer to call it. Okay. Your book says weight, tomato, tomato, whatever. So that again is the number of protons plus neutrons. So let's go back to this example. Is the number of our protons plus our neutrons 4.003? No, it's just 4. Why isn't it just 4.0? Why isn't it just 4? The reason that it's not 4 is that some elements have what are called isotopes. So an isotope, right, have varying numbers of neutrons. So remember, you can't change the number of protons without changing what element it is, right? So if you gained or lost a proton, of helium, it either becomes hydrogen or whatever 3 is. What is 3? Why do I not know that? Because it's been a million. Lithium. I was like, it's an L something. Right? It becomes a different element if you change the number of protons, okay? Because that's what defines them, okay? Is their atomic number, okay? But any given element may have variety in the number of neutrons. And so the reason that helium has an atomic mass of 4.003 is because on average, there are some isotopes of helium that have an extra neutron. Most of them don't, which is why it's 4. But there's a very, very small number that do. So that's why it's 4.003. Okay, so that's why it's not exactly 4. Okay, and so if we look at our, back to the periodic table, right? All of these guys have 55.85, right? 26.98, right? So because there's isotopes, okay, there's some versions of that particular element that have more or fewer neutrons, okay? All right, that's why it's not a whole number. Okay, so that's what an isotope is, okay? Now, the way that we always draw atoms is we draw them with the nucleus and then a ring to represent the electrons, and then we put in like little dots for the electrons. In reality, though, it's not a ring, it's more like a cloud. Electrons are moving so fast that you cannot pinpoint exactly where they are. They're basically like this blurry cloud, okay? So a more sort of, your book is now using a more sort of realistic representation of what an atom might actually look like, right? And so in this particular one, you know this because it tells you, but you could also look it up. So this is nitrogen, right? Nitrogen has 7 protons, 7 neutrons most of the time, but let's go back to this for a second. If we go back to nitrogen here, look, its atomic mass is 14.01, which means that some isotopes of nitrogen have an additional neutron. A very small number of them, but some do. Okay, so 14 and a little bit, okay? And then 7 electrons, right? And so they're showing the electrons kind of in this like blur, essentially, okay? All right. So that's what they really look like, is like a blur. But the way that we illustrate them is with rings, because it's just easier to like think about when you're thinking about how different atoms interact with each other, which is what a chemical reaction is, right? So chemical reactions are when atoms are interacting with one another, and there are several kind of rules for that. And because this is not a chemistry class, I'm going to oversimplify it quite a bit. But that's okay, because that's all you need, right? Is enough chemistry to understand biology. That's all we're doing. Okay. So remember, our 4 most, common elements that are found in living things are hydrogen, carbon, nitrogen, and oxygen. And so here they are, and their atomic number is listed, each one. And so you can see that inside of the nucleus, right, are protons. So hydrogen has 1 proton, doesn't have any neutrons. Usually it can, but it usually doesn't, right? Carbon has an atomic number of 6. So it has 1, 2, 3, 4, 5, and then the other one's on the back. 6 protons, and then 1, 2, 3, 4, 5, and then the other one's on the back. 6 neutrons usually, but it can actually have 7 or 8 too. Okay, you get the gist. Okay. And then where do the electrons go? So the thing about electrons is that electrons always fill in these like shells around the nucleus of the atom. The first shell can hold up to 2 electrons, period. Okay? Any electrons beyond that are going to go in the next shell. That next shell can hold up to 8. You're thinking to yourself, what if an atom has more than 10 electrons? Then what, smart girl? Then what do we do? Then there's another shell. But quite frankly, since we're doing biology, we're not concerned with a lot of those really, really big atoms and like what their electron shells are about, because we just don't care. Right? So, I mean, we could get into it, but we're not going, I don't want, there's no reason for us to do so, because the biggest thing we're going to be talking about is oxygen. Okay? So all you have to remember is the first shell holds 2 electrons. The second shell holds up to 8. Okay? Another thing you need to know about these electron shells, or some people call them valence, right? That basically means the same thing as like, it's like shells. Okay? So the valence electrons, the electrons in the shells. Okay? The second thing you need to know about that is that the inner shell always, under normal circumstances, always fills first, and then the remaining ones end up in the outer shells. Okay? If it helps to remember that, one important thing to kind of remember is that, remember, electrons have a negative charge and protons have a positive charge, right? So because of the interaction between the positive and negative being attracted to each other, like a magnet or anything else, right? Because of that positive and negative being attracted to each other, it would make sense that as many electrons as can fit in that first shell will, because there's a big old pile of positive stuff right there, right? So that first shell, that inner shell, fills first, and then you go from there. Okay? Okay. So in hydrogen, you have the 1 proton in the nucleus, and usually it doesn't have any neutrons. And then you have 1 electron in that first shell. Remember, it can hold up to 2, so you have this little empty spot. So we often do a little empty spot just to kind of remind ourselves, oh, there's a space here for another one. Okay. All right, carbon. Carbon has an atomic number of 6. So that means you have 6 protons in the middle and neutrons, right? So then how many electrons do we have? Also 6. So we have 2 in the first shell. 1, 2. Then we have 3, 4, 5, 6 in the next shell. And we have a bunch of empty spaces, because remember, that shell can hold as many as 8. So how many empty spaces do we have? Okay? Assuming we're good. If not, you'll talk to me. You'll tell me that you're confused. Okay? All right. Nitrogen has an atomic number of 7. So that means 7 protons. Okay? So then we're going to have 7 electrons too. Okay? So 1, 2, 3, 4, 5, 6, 7. So how many empty spaces do we have now? 3. Yeah? So oxygen has 2 empty spaces. Okay? Why do empty spaces matter? Well, atoms are most stable when their outer shell is full of electrons. What do I mean by stable? When I say stable, I mean they're not going to react with something else. Okay? So an atom that has a full outer shell is non-reactive. It's not going to react with any other atoms. If it has openings, though, it will. Okay? So, right? It's like, I'm trying to think of a good example for this. I'm having, and the only example I'm coming up with is really like sad and pathetic, right? It's like those people who, you know, are so lonely, they have an empty spot inside and they need to fill it with somebody. I don't know why that's the place that I go, but there it is. Okay. So they have these empty spaces, right, in their outer shell that they need to fill. Okay. The way they fill those varies. Okay. And so that is what happens in chemical reactions. Okay. All right. So one way, let's not get ahead of myself. One way that we can fill those openings in the outer electron shell, right? One way we can fill the empty spaces is by stealing an electron from another atom. Okay, let's look at that. All right. So here we have sodium and chlorine. Excellent. Okay, let's go look those up real quick, shall we? Let's go back to this. All right, sodium. Sodium is Na. Hold on, and it's going to be green because it's important in living things, and then there's chlorine there. So sodium has an atomic number of 11, and its atomic mass is 22.99, so maybe we'll just call that 23. Chlorine has an atomic number of 17, and its atomic mass is 35.45. Okay, I'm going to write those down so I don't forget. So chlorine is 17 and 35 and a half. Chlorine, that was chlorine. Sodium is 11, and we're just going to call that 23. We're going to round up, you know, imprecise. Okay, cool. All right. So if we know, I'm going to write this down here. So sodium, just copying my little notes down. All right, chlorine. Okay, so if we know that the atomic number for sodium is 11, what does that mean? Inside the nucleus, we're going to have 11 protons. Yeah? Okay. Now, the atomic mass or atomic weight, what was that again? It was the protons plus the neutrons. So if the protons plus the neutrons is 23, and we know the protons are 11, that means how many neutrons are there? Most of the time. I know that's tiny, so I'm just going to write it up here so you can see it better. So 11 protons, 12 neutrons, where it says Na, right, in that little nucleus. Yeah? If you're struggling with that, you know, ask. We can do examples and stuff in like Zooming if you need help. Okay. All right. Sweet. Okay. So that first shell. So that's what's in the nucleus, right? That first shell. How many electrons are in the first shell? So we're gonna have a total of 11 electrons, right? So 1, 2. How many are in the next shell? 3, 4, 5, 6, 7, 8, 9, 10. So 8 more in the outer shell. So 8 plus 2 is 10. And we said there was 11. So then there's going to be the 11th one is out there on its own. And that third shell can also hold 8. So that's not ideal to have like one old electron like all out there by itself. It's not ideal. Okay. All right, we're just going to leave that alone for a sec. Okay, now let's look at chlorine. So chlorine has an atomic number of 17. So that means we have 17 protons. And the mass is 35.5. Okay, whoa, that's crazy. All right, let's look at a calculator. Okay, 35.5 minus 17. What does that equal? Okay, that equals 18 and a half. So I'm just going to say approximately 18 neutrons. Could be 19, could be 20, whatever. Yeah, so the neutron number can vary, right? That's what an isotope is. Okay, so there are different isotopes of chlorine. Okay, sweet. And then if we have 17 protons, we also are going to have 17 electrons. Okay, I hope you're with me so far. All right, so let's count those electrons. So this stuff is all in the nucleus, of course. Alexa is talking to me. Alexa, stop. What did she hear me say that she felt like she needed to insert herself in my conversation? That's creepy. I probably shouldn't have Alexa in my bedroom. That's scary. Anyway. Okay, what was I saying? So electrons, let's count our electrons, right? So the things that I circled are in the nucleus of each atom, right? So let's count our electrons. Okay, so we're up to 17, right? So we got 1, 2. First shell has 2. 3, 4, 5, 6, 7, 8, 9, 10. 8 more, okay? 11, 12, 13, 14, 15, 16, 17. Oh, look, we have an empty spot because we have 7 in the outer shell. And then we have an empty spot. Oh my gosh, and I'm about to get interrupted again. It's a small man. Let's see what he needs. Dad's not here, and it was vitally important that somebody shuffled his Pokemon card deck at this moment. It's done. Crisis averted. Now the cat's looking at me like he wants to interrupt too. This is just going to be one of those lectures. Where were we? Okay, so we have an empty spot. Huh. Also, not the most stable situation. Okay, so if you had one too many of something and you really wanted to get rid of that one thing because it was just like extra and a pain in the butt, and your friend desperately needed another one of that exact thing, you might just give it to them, right? Because that would make everybody happy. Thus is the nature of an ionic bond. Okay, so what happens in an ionic bond is one atom gives one or more electrons to another atom. Okay, so one atom gives, I'm going to say 1 plus, 1 or more. I shouldn't say that because you're going to be plus proton. 1 or more electrons to another atom. So in the case of this particular example, the sodium has that like dangly electron on that outer shell that's not stable. It's extraneous out there. Chlorine desperately needs 1 more to become stable. So the thing that sort of makes the most sense for everybody concerned is if sodium just gives that one to chlorine. Chlorine just takes it away. Yeah? And now they're both super stable because now, right, sodium gets rid of that third shell that only had 1 electron in it, right? And chlorine, its third shell is full. So now everybody's stable, right? So good. Okay. The result of an ionic bond, though, is that this produces something called an ion, hence the name ionic bond. Right? So what an ion is when the number of protons and the number of electrons in an element are not equal. Okay? So the definition of an ion is when protons and electrons in an atom are not equal. Okay? So both sodium and chlorine are now ions, okay? You notice here that next to sodium, there's a little plus. Why is there a plus? Next to chlorine, there's a little minus. Why? Why is that? So normally the number of protons and electrons matches, right? But if you're giving away or stealing somebody else's electrons, then that number is not equal anymore, right? So how many protons does sodium have? Remember, the number of protons doesn't change. So it has 11 of those. How many electrons does it have? Now that it's given one electron away, now it has 10 electrons. So sodium ions overall have a positive charge because they have one more positive than they do negatives, right? So 11 positive minus 10 negative, right? You end up with 1, right? So overall, it's a positive ion, okay? Whereas the chlorine, what did we start off? We start off with 17 protons. How many electrons does it have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now it has one more, electron than it does protons. So it is negative. Yeah? So the name of this compound now, we call it sodium chloride because instead of chlorine, because when you have a negative ion, instead of it being called ene, you call it ide. You don't really need to know that. I'm just telling you why. Okay. The ramifications of this are that oppositely charged ions are attracted to each other. Right? So positives and negatives attract, right? So if you have a positive ion and a negative ion, they're pretty strongly attracted to one another, okay? So that's an ionic bond, right? So in this one slide, we learned a bunch of different things. We learned more about how to figure out the makeup of an atom. We learned what an ion is, and we learned why ions happen, right? So you're either gaining an electron or losing an electron so that outer shell is full. And then because now you have an unequal number of protons and electrons, you're either positive or negative, depending on which one you have more of, right? And furthermore, then you're going to be attracted to something that has the opposite charge. Okay? So that's ionic bonds. So that's not too bad. Okay? So that's all right. Okay? So, here's another way of looking at that, right? So we've got our sodium there with its, 11 electrons, awkward number, 10 is better because then you have 2 and then 8 and that's 10. We have chlorine, which has 17 electrons, awkward number because it's got 2 and then 8, so that's 10, and then it's got 7, so it's got an empty spot. So the sodium donates an electron to the chlorine, okay? And then the sodium has a positive charge, the sodium ion, and the chloride ion has a negative charge. And so then they're attracted to each other. So an ionic bond is the attraction of opposite charges that holds two ions together. Okay? In this case, sodium chloride, which is table salt, right? So it sounds fancier when you say sodium chloride, right? But yeah, so salt. This is salt that you eat. Okay? Cool. All right. So that is an ionic bond. That is the first type of bond that we are going to learn. Okay? All right. The next type of bond that we're going to learn is called a covalent bond. So let's think about that word covalent. Covalent. So I talked about how those shells are sometimes called valence shells. So covalent. What do you think that means? Covalent. So co usually means you're sharing something, right? So if you are not married to the other parent of your child, you might refer to them as your co-parent. Sometimes I call my husband my co-parent, even though we're married. I'm like, yeah, the co-parent did this. Okay, right? So co means you're sharing something, yeah? So covalent bonds are when atoms are sharing electrons. Why share when you could give them away? I'll explain. Okay, so there's a couple different examples here, and they're also trying to show you a few things with this example. They're trying to show you the actual like configuration of where the electrons are with the, you know, the little shells, right? They're also showing you, and this is how we often write the structural formula, and this is what it looks like if you have a space filling model or a ball and stick model. I don't really care about all that model crap so much, okay? Whatever. Okay, let's look at one of these examples. Let's look at hydrogen. Let's start with that, okay? So let's go back to our periodic table. Whoop. So hydrogen, 1 is the atomic number. It has 1 proton. And the atomic mass is 1.008. So that means most of the time it doesn't have any neutrons. It's literally a proton in the middle, an electron around the outside. Okay? All right. Actually, this isn't the best example. And let me tell you why. The reason this isn't a very good example is that hydrogen does easily let go of its electron. And then it has no electrons at all. It's literally just a proton. That's weird. Okay, so instead of looking at hydrogen, let's look at this other example, this example of oxygen. Okay, so let's go back and get the deets, get the stats for oxygen, and then we'll come back and talk about the bond that it forms. Okay, so oxygen has a atomic number of 8 and an atomic mass of 16. Okay, so let's go back to here. Okay, and I'm just gonna pop in a white screen for a minute. Okay, so what did I say, 8 and 16? So oxygen, 8, 16. So that means it has 8 protons, and assuming that, you know, everything's normal, 8 electrons too. And because it has an atomic mass of 16, that means how many neutrons does it have? Do, 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 do. There you go. Okay, so we have our nucleus. That's what's, oop, nope, wrong. What are you doing, Sarah? What are you doing? You're out of control. That's what's in your nucleus. I'm not going to draw 16 little, I'm not going to draw 8 little pluses and then 8 little n's, but that's what's in there. Okay. All right. What's the deal with the electrons? So we got our first shell. Yeah. Okay, so there were 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. So it has 2 empty spaces. Well, it's possible that oxygen could find some other element that it can steal 2 electrons from. But it's a little bit harder to steal multiple electrons. It's usually, it's not as hard to steal 1, but stealing multiple is kind of tricky. Okay, so if oxygen happens to come into contact with, let's say, let's you know, not do the example that's in the book. Let's pick another example. Let's say hydrogen. Okay, we know hydrogen. Hydrogen is 1 and 1, right? So that means it's got 1 of these, it's got 0 of those, and it's got 1 of those. I shouldn't write things in a different order in the 2 places. Messy. H is 1 and 1, so it has 1 proton. It has 1 electron. It has 0 neutrons. Sweet. Okay, so let's say we have a hydrogen over here. There's its nucleus, which has its single proton in it. Here's the electron and the empty space. Here's my hydrogen. Empty space. Oh. I'm going to ignore the neutrons for now and just, you know, remind ourselves how many protons are in the middle. Huh, look at that. That's interesting. Right? So, what could we do here? Well, this is actually whoa! I didn't plan ahead. That's what happened. I just deleted my white screen. Dang it. That's what I get for touchy. It'll give me an opportunity to redo it. So rewind if you want to go back and look at that again. I'm going to add a new white screen here. Okay, so I'm going to redo that. So my oxygen has 8 protons in the middle. 1, 2. God, it's an ugly 8. Let's try that again. 1, 2 electrons. 1, 2, 3, 4, 5, 6. Empty spot, empty spot. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 2 empty spots, right? And then here's my hydrogens. Empty spot, electron, electron, empty spot. So one of the things that often happens, instead of stealing electrons from somebody, sometimes you just share. So if these two things get close enough together, they can share the electrons in their outer shell, right? So they're basically, what happens is, because remember, electrons are like in a cloud, right? They get close enough together that the clouds overlap. And that makes them super stable because they've got this shared cloud, right? So what ends up happening, this is called a covalent bond, right? Because they are sharing valence electrons. So one of these electrons is contributed by the oxygen. The other one is contributed by the hydrogen, but it don't matter because they're both sharing both of them. Okay, so that's a covalent bond. And so take a mental image of this because it's going to go away as soon as I change. Okay, so we're not looking at an example of that specific molecule, although we will be in a second. Okay. But here are some others, right? So if a hydrogen and a hydrogen come together, each one only has 1 electron. So if they share them, right, then collectively they have 2 electrons in their outer shell, right? What happens with 2 oxygens get together? They do something weird. They do something called a double bond, where they end up sharing 2 pairs of electrons. So they're not just sharing 1 pair, they're sharing 2 pairs. That's kind of weird. Okay, you can draw it out if you want to. I'm not going to take the time to do that, right? Here's methane, famous for coming out in cow farts. It's a greenhouse gas, right? Okay, this guy. So the carbon, remember carbon is 6 electrons, so it's got 2, and then 1, 2, 3, 4. And then each hydrogen only has 1, right? So carbon is 6 plus 1, 2, 3, 4, 5, 6. And then each hydrogen, right, has its 1, 1, 1, 1. So they're sharing electrons. So nobody's giving away. Carbon especially doesn't typically form ions, because in order for carbon to form an ion, it would have to gain or lose 4 electrons. And that's a lot to gain or lose. So typically it's only elements that have either 1 empty space, sometimes 2, or 1 or 2 extras, right, in that outer shell that will form ions. Okay, so these are covalent bonds, right? And so if you need practice with all of this stuff, you can totally do that. That's fine. Okay, so this is the covalent bond that I drew. This is prettier than mine. Right? You can take the time to look at this and figure it out and like figure out what's going on. Okay, so shared pair of electrons is what you're seeing here. So covalent bonds are when you're sharing electrons. So that was our second type of chemical bond. So ionic bond, chemical bond, or covalent bond. All right. Okay. Now the absurdity begins. What do water and Mickey Mouse have in common? Their shape, right? So water molecules, if you hold them the right direction, look quite a bit like Mickey Mouse. So think back to my drawing a second ago. If I turned it, instead of facing to the side, if I turned it and pointed it up, it would look like Mickey Mouse, right? So the reason that water has this shape is, remember that you've got 8 protons in the middle and then neutrons too, but we're not really concerned with that right now. You got 1 electron, or excuse me, 1 proton inside each of those nuclei. And then we got our, our shell of 2. But then there's sharing happening, right, between these guys. And so the electrons, 1 from each hydrogen, and the 6 outer electrons from oxygen are gonna, because this is what they do, are gonna swirl around because they're shared, right? It's covalent, okay? Now, the really interesting thing that happens with some covalent bonds and not others is the distribution of the electrons, okay? So just real quick, let's just tally up how many protons we have, how many electrons we have. So we had 8, 9, 10 protons total, right? 8, 9, 10. 8 from the oxygen, 1 from each hydrogen. You can go back and look at the structure of oxygen again if you need to, okay? How many electrons do we have? Well, also 10. We don't care, we don't care about the number of neutrons because we don't care, right? So overall, this is not a charged, this is not an ion that we're looking at, right? This is not a charged thing because we have an equal number of protons and electrons, okay? But one really interesting thing in this specific type of covalent bond, because remember we're sharing electrons, is what happens is the electrons, they don't spend their time equally, right? With the 2 hydrogens and the 1 oxygen, okay? So, right? So it's like if they're sharing the electrons, but the electrons spend more time in one place than another. So I'm going to go back to custody, right? So in the summer, parents have shared custody, but it's summer, the kids really want to hang out in the pool. Yeah. So maybe they're going to try to spend more time with whichever parent has the pool. Right? Okay. That's what's happening here. But instead of a pool, right? What happens is electrons, remember, have a negative charge, and negative charges are attracted to things that are positive, right? Well, oxygen has a big old pile of positive in the middle of it. It's got 8 positive things, 8 protons in the middle of it, whereas each hydrogen only has 1, right? So the electrons, even though the total number of electrons and the total number of protons are equal, the electrons are much more attracted to the oxygen than they are to the hydrogen. That's why there are those 2 yellow arrows that are pointing that way, right? Because that ball of 8 protons is way more attractive to the electrons than one little dinky, proton off over there. Okay. So that's why when I was drawing it, I was like, there's so many down here, right? Because they spend way more time with the oxygen than they do with either hydrogen. So what does that mean? Well, this produces something that we call a polar covalent bond. And a polar covalent bond, I should have written this so I could written it over here so I could write the definition, sorry. Okay, is when the electrons spend more time on one side of the molecule than another. right? So the electrons spend more time down on Mickey's chin and less time on Mickey's ears because they're much more attracted to Mickey's chin. Does that make sense? Right? So they're more attracted to this. So they hang out down here more. They come up here too. They're sharing, but they're more attracted down here. Okay? So equal number still. We don't have a charge in the sense that we don't have a this is positive, this is negative, like overall situation, because the number of protons and the number of electrons is equal. But it's negative-ish on Mickey's chin. That's what this means. Right? That Mickey's chin is slightly negative because the electrons spend a little more time down there. And Mickey's ears are slightly positive, right? Because the electrons spend a little less time up there. Okay, does that make sense? I hope that makes sense. Okay, so that's a specific type of bond called a polar covalent bond. Not all covalent bonds are polar. Okay, some covalent bonds, they're sharing the electrons completely equally. In fact, all of these examples are non-polar covalent bonds because they share electrons equally, like perfectly equally. Okay, so all of these examples are covalent bonds that are non-polar, so non-polar covalent bonds, as opposed to water, which forms a polar covalent, well, forms polar covalent bonds between the oxygen and the hydrogens. Okay, I hope that makes sense. All right, so there's a non-polar example, equal sharing of electrons. There's a polar example, unequal sharing of electrons, right? And typically the way that we write that, like I said, is we do the like plus in parentheses, the minus in parentheses. This way they put it upside down because, you know, I think they don't want to get sued by Disney for trying to look like Mickey Mouse. Disney's really protective of that shape, by the way. They sue people like crazy. It's like, it's 3 circles, dude. How can you sue people for using 3 circles? Disney has good lawyers. Yeah? Does that make sense? Okay. If not, we'll talk about it. Okay? Talk to me. Okay, so that's polar covalent bond. All right? So, recap. We've talked about covalent bonds. Before that, we talked about ionic bonds. There is a third type of bond that I want to talk about. And those are hydrogen bonds. Of the 3, hydrogen bonds are the weakest of the 3 that we're going to talk about, okay? Because hydrogen bonds form between molecules that are polar or molecules that are charged, okay? So my best example of this is water, right? So, and this is something that you fundamentally appreciate without really thinking about it, okay? So let's think about water for a second, okay? So water, if you have a bottle full of water, why is my Fitbit burning? Oh, I'm getting text messages. It's interruption day. Okay, so there's water in my water bottle, okay? When I'm splashing the water around, what that means is that the water molecules are all moving around, okay? Well, water molecules actually are kind of attracted to each other. Not a real strong attraction, but a little bit of an attraction. And the type of attraction that forms between water molecules is called a hydrogen bond, okay? So each one of these things, there's 5 little blobs. Each one of those is a water molecule, right? Each one is an oxygen with 2 hydrogens, right? So each one is an oxygen that has a polar covalent bond with 2 hydrogens, okay? So remember, what that means is that Mickey's ears are going to be slightly positive, and Mickey's chin is going to be slightly negative. So what does that mean for water molecules? Well, if you have a bunch of water molecules together, what that means is that Mickey's chin, this Mickey, his chin is going to be attracted to this Mickey's ear. And this Mickey's chin is going to be attracted, yeah? This Mickey's chin is attracted to this Mickey's ear. This Mickey's chin is attracted to this Mickey's ear. This Mickey's ear is going to be attracted to this Mickey's chin. The transcript for this is going to be a nightmare because I said Mickey 14 times. Anyway, yeah? So that's a hydrogen bond. So a hydrogen bond happens between different molecules, okay? So hydrogen bonds form between molecules that are polar or sometimes charged, okay? Right. To kind of summarize here, how strong are these different bonds? Covalent bonds are the strongest because remember, they are, when we're talking about covalent bonds, the atoms are like full on like sharing electrons, right? So it's like they're sharing their electrons, so they don't come apart very easily. If they're like full on sharing electrons, they don't come apart very easily, okay? Ionic bonds, they're attracted to each other because positive, negative, right? But, you know, if another positive or negative thing came along, right, they would leave. Okay, so it produces what we call a compound instead of a molecule. Okay, because they're not sharing electrons. One gave its to the other one. Yeah, so the sodium gives its electron to the chlorine. I can talk. So we call that a compound instead of a molecule. Sorry. Right, and then hydrogen bonds are the weakest, and you know this because you can break them real easily. I just have to blow on some water and I can break them, and I can break the hydrogen bonds. Yeah? Okay. So those are our different types of chemical bonds. Okay? So I'm going to stop here because this is a good place to stop. And so the next thing we're going to talk about is we're going to talk about the magical characteristics of water. Not really magic, but just amazing. How about that? Amazing characteristics of water, right? And so we're going to talk about water for a little bit, and then we're going to start talk about the really big molecules that are found, that are sort of the most abundant molecules in living things. Okay? All right.